discussion about the realm DMA system, aka the memory transfer system. So I was going to start with a quick reminder, a little bit of what we talked about last week, so that people could page back in any questions they wanted to ask, and then we can continue. So all the stuff for the DMA system lives in this transfer subdirectory of the realm runtime source tree. And we looked at kind of the four main files are transfer.h and cc, which are responsible for taking copy requests from Legion or something else above realm and analyzing them to figure out exactly how they should be implemented as a single or multiple hops through the memory hierarchy. And then today we'll look a lot at channel.h and cc, which are responsible for the actual implementation of those of each of those hops that are decided. So we spent a lot of time last time looking at the path of taking a copy and doing this horribly large function here called perform analysis, which is how a transfer description, which is part of essentially the compiled form of a copy request, goes through the various fields, and for each field figures out what hops are going to be used, and basically builds up what's called a transfer graph. Let's see if I can remember. So here's an example where we start adding things to the transfer graph of one node for each kind of copy that's going to be done, and edges for the data that flows between two nodes in a multi-hop copy. And there's paths in here for gather and scatter. There's a standard path. There's a path for fills, and then there's kind of the standard main path, which is this one here, which knows how to merge together multiple fields when you're doing kind of simple copies. And we talked also about this find fastest path thing, which is once you know that you've got data flowing from a given source memory to a given destination memory, this is the helper function that basically says, find me the fastest direct or multi-hop path from that location to that other location. And we'll go into that in a little bit, but first I wanted to stop and see if people had questions from last time, because this is about where we stopped last time.
So you only you're doing individual fields. You don't, like in AOS copies, is there a separate path for fusing like fields together in the graph?
No, so this is not, basically this path here does multiple fields.
Okay.
The outer loop is iterating over fields, but what this loop is able to do is say, okay, are there other fields that basically match it in every way other than just what field ID they are?
Okay.
If so, they get merged together here and done as well.
Okay, and you treat those like as you sort of merge fields together into like a fused field effectively that you're going to copy.
Remember if we do that right anymore. I'm actually not sure that works properly for AOS anymore. We used to have a mode for it, and I think actually that's an optimization that still needs to be done if copying all, either all the fields or at least consecutive fields of AOS is common again. For a long time, it wasn't very common.
Mm-hmm.
Do we have major AOS use cases running around these days?
I don't think there's a lot of use cases, but I do know that there's like a few applications that will switch back and forth. I mean, at least in Korean American stuff, I don't think you see any of that.
Okay.
But because I don't think we do a lot of compound type arrays at the moment, but you might see that at some point.
Yeah. Okay, so what this code isn't doing that it could do is it could be looking at, okay, once it's got a bunch of fields all coming from the same source into the same destination instance, it could look at whether they are in fact contiguous. Mm-hmm. And if you've got things that are contiguous in both source and destination, then it can merge those together. Mm-hmm. If in the general case you've got some that are contiguous and some that are not, you'd really like to do that as two separate copies, I think. Mm-hmm. Because you wouldn't get much benefit of just fusing, some of them if there's basically what you want to come out of the end is kind of regular copy patterns. And so if you have regular strides between things, those turn into rectangles.
Right.
But if you've got a stutter because it's, these two consecutive 4-byte fields and then this other 4-byte field, which is different from the first 4, then you prefer you'd like to do all the 8-byte ones and then come back around and do all the 4-byte ones.
Right.
So I guess that would be on the list of it. We could start doing it once somebody had an AOS case that needed it.
Yep.
I will say, right, the code here is basically a bunch of pattern matching cases. Yes, and even in the find fastest path thing. So it's a lot of, when somebody says they have a case that matters, then we can go in and add another pattern to match here. And unfortunately, the way this code is written right now is all the patterns are in one big function. Really, this thing should be refactored so each of those patterns is kind of done as a separate function, and it's not quite so hard to find your way around in it.
Mm-hmm. And does find fastest path take into account transposes? Like if I'm transposing dimensions or transposing AOS to SOA? I guess let's not worry about AOS to SOA. Let's do the dimensions.
That's right, and it does, and that's because of this fragments thing we talked about. That basically, once we've chosen a dimension ordering, right? That we're gonna, if we're doing a multi-dimensional copy, we're going to pick what order we're going to iterate over the points in the copy domain.
Right.
And once we've chosen that, we then basically go say, okay, how many contiguous pieces of data would that result in? If we're able to do only contiguous 1D copies or 2D rectangles or 3D rectangles. And that's what this frags array is. It's got it's an array of, I think, max dim plus 1 or 2, because essentially fields become another dimension. And what it says, so for each of those, it basically describes how fragmented the data is going to be. And when you have a transpose, what you'll see is data that's really fragmented in one dimension, not so really fragmented on source and not on destination, or vice versa. It is the case that we choosing a dimension order favors the destination right now. So we prefer to fragment the source rather than fragment the destination. But the rest of the code doesn't actually care. It's just that it's usually a little faster if you fragment source but not destination.
And if you pick the copy domain ordering, like the order you're going to iterate over the points, the copy domain based on something, or just is it sort of chosen heuristically?
No, it is. I'll go back up to it. It's a little bit higher up here. Choose dimension order. It's based on the actual layout knowledge. So
so it actually looks at the sources and dests and figures out. Yeah. Okay.
That's right. Now one thing we do though, which is suboptimal in some cases, is that we pick one dimension order for every single pair of fields.
Yeah.
No.
Oh,
for globally for the whole graph.
Oh, I see. Okay,
in theory, if you had, right, because sources and destinations can be different instances, right? In theory, if you had a copy request that was moving some fields from row major to row major and other fields from column major to column major, then you would like two different dimension orderings.
Right. One
for the row major ones, one for the column major ones. And this code here is not smart enough to split that out yet.
Okay.
Again, nobody's done it yet, so very event-driven here.
All right.
Any other questions on this stuff?
I'll stop monopolizing the questions.
That's fine. Shows interest. Okay, so let's real quick go look at find fastest path. And the catch is it's not even in this. Wait, what it was? There it is. Okay. Typos are fun. Okay, so as I said, this is that helper function that says, for any given, once we've got one or more fields that we want to go from a given source memory to a given destination memory, maybe with serialization, maybe with reduction ops, and knowing how fragmented they are, this is the thing that says go find the fastest path between those things and store it in this mem path info. And this is basically just going to be a list of what memories to go through and also what channels are going to perform the transfers. And as I said, we'll talk about channels in most of the rest of this meeting. What this amounts to is basically a minimum path search in a graph with the complication that the costs on the edges are a function of these parameters here, the total bytes moved and the fragments. And so you basically need to do it's done as effectively it's not a star. It's a pruned breadth first search effectively of the possible paths you take through the tree. But it's heavily pruned, so anything that exceeds the first thing it does, for example, is it says is there a direct path? And if there's a direct path, then we remember that, and that becomes the upper bound. Any other path that exceeds the cost of the direct path won't be considered at all. The other major pruning that's done is that the code currently assumes that if you've got a copy from between two memories on the same node, that it will never be profitable to leave that node. And so it only does a search within the paths available on that single node. And similarly, if you've got a path that starts on node X and ends on node Y, then the search assumes that there will be exactly one exactly one hop that goes from a memory on node X to a memory on node Y, and there will be no other nodes involved. And so basically it becomes two local searches with one internode hop in between. And so basically the way that comes out to is it does a local search on the first node of basically what's the fastest it can get to any of the memories on the first node, whether it's the intended destination or whether it's some intermediate memory. And then
how hard would it be to add network topology in there? I mean, is it just a matter of changing the graph and the search criteria, or is there something more fundamental that makes that hard?
So it depends how you want to add it. If you just want it to be that different hops are slightly different in cost, then the cost model for those internode hops could easily say it has a different cost if you want to go from, say, GPU 0 to GPU 0 versus GPU 0 to GPU 5. The thing it can't do is it doesn't know how, if the difference got so large it made sense to bounce off an intermediate node.
Right.
That would be hard because even opening up that search adds another order n to the cost.
Right.
So that's something we'd have to watch out for. And actually, there have been some folks working with Stanford that have asked about this, and the answer is it's not easy. So it would have to be heuristics of probably. I think what you would do is you would do something that responded on you let the search think it's still going from X to Y, but the thing that when you ask a given channel, hey, what does it cost you going X to Y, it would give a cost that actually goes through Z. And then you'd have to say, okay, well, if we choose that, then we know that we add those two hops as one when we enumerate them later, rather than searching through all the possible Z's at this level here.
And I mean, in some cases, like you could almost determine the path by which NIC you send the stuff out on, right? I feel like that might be an intermediate proxy instead of modeling like the whole network.
And if that's just a GPU 0 would rather talk on this node, would rather talk to GPU 0 on that node.
Yeah.
Right. Then that's something we can do with the
existing
with the current stuff. Because basically what it does is once it's found the path to each intermediate buffer on the source node.
Right.
And then says, okay, from every intermediate memory on the source node to every intermediate memory on the destination node, what are the costs of those things? And therefore, what is the cheapest way to get to each memory on the destination? And then from there, it's on the destination. Now we can stay in just the destination node and ask, okay, from each of those possible landing points of the internode copy, how fast can we get to the actual destination?
Right. And you're not modeling the NICs though right now, right? Like it's just a node to node.
The network module just says every hop between the two nodes is the same.
Same. Okay. All right.
Which is not perfect, but we haven't actually seen any cases where that's the limiter today.
Okay.
On a heavily NV-linked machine, you could imagine it being, you wanting to stay on the same rail on the network.
Right.
For example, on say Selene, and we're not smart enough to do that right now.
Okay.
Okay. This search is expensive enough though that we do have this LRU cache in front of it. It's a bit of an expensive cache because it does need to match on basically all of these arguments here. Right? It's not every path can be different. So really, we're matching on effectively the exact same copy being done more than once and remembering the path. The transfer descriptor was originally intended to be the way that memory would be done. If you're going to reuse a copy as part of a subgraph multiple times, then we would never even call find fastest path more than once. We would just remember the compiled transfer graph. But in CUDA today, right, we're not able to use tracing, which means we're not able to use subgraphs, which means that we do have to call find fastest path for each iteration of the same copy, which means a cache that remembers what the answer was on an exact match is a good thing. So that's what's going on in this LRU code here. as I said, here's the basic search. We look at the direct path. If it works, we record that as a baseline. And then the multi-hop search. And this is important, right? Even if the direct path is there, we search for multi-hop paths. And the reason is twofold. One is that sometimes, actually, the main reason is compaction. Or transposition. If you're going to do a transpose, you might want to transpose, say, in system memory before going over to device memory. Or now that we can transpose in device memory, you probably actually do it the other way around. You would copy contiguously and then transpose, rather than having a transposing copy that crosses uses could-around copies. But so basically, we search this, but we do aggressively prune anytime here. For example, right. If a cost for a given path is not better than the direct cost, then we throw it away immediately. We don't even bother propagating further, because it can only add to the cost. So the individual hops is this best channel for mem-pair thing. And so whereas this overall thing was finding the whole graph, this is the thing that says finding the best channel for getting from a given memory directly to another given memory. And this will be the segue into what channels are. But the way this works is this searches over. It can be the case that multiple channels may know how to copy from the same memory to the same other memory, and so we choose the one that's the cheapest. And then it's also the thing that returns what channel is being used. And if a channel is being used, then I talked before about there's this because channels are polymorphic objects. We build this, which maybe we don't do that here. Here we just remember the channels. Later on, we turn that channel into basically a constructor function to build a transfer descriptor in the transfer graph. There's a heavy amount of logging in this, which is, so whenever anybody says, hey, my copies are running abominably slow, it's this XPath logging I turn on, which is basically describing the entire search it does and why it chose the path it chose, which is often educational. Okay, so as I said, this search is pretty expensive. The OLU in front of it has made it a lot cheaper. It still feels like there could be ways to be a little bit more intelligent about this searching, understanding how that certain combinations of paths will never be profitable. But that's a little complexity we haven't had to do yet. So it's not done yet. Okay. So the end result of this, right, is that we have we performed the analysis based on splitting up the fields and finding the fastest paths. And once we've done the analysis, then we declare that the copy, we have the metadata we need to do the copy. So we come down to the end here, and we're going to mark that the analysis is complete. Because the transfer description may be used by more than one copy, we have to basically resolve the fact that some of the copies that want to use this will already be known, and so those will be in this pending ops list. But it may also be that there may be copies that come later that want to use this description after the analysis has already been done. So that's why we mark the analysis is complete. And for the ones that are done, they go to the next stage called allocate IDs. If a new copy comes in that sees that its analysis is already complete, then it'll call allocate IDs itself. This is a recently added method for predication stuff. This is the path that says if it turns out the precondition for a copy is canceled, is poisoned, then this is the thing that basically skips the analysis. And we mark that it's complete, but but that it was not successful. So that basically any copy dependent on that is also going to fail. So once we, let me see. Okay, sorry. So as I said, the next step is allocating IVs. So the other precondition for allocating IVs is we do have to know that before we start actually allocating any of the intermediate buffers we're going to use for copy, we have to know that we're actually going to do the copy yet. So any data preconditions for a copy are also must be satisfied before we call allocate IDs, which is why there's a couple different paths to this. But either way, once we get here, we're actually starting the copy. And the first step of starting the copy is performing the allocation of any or all intermediate buffers that we're going to use as part of any multi-hop copies. So we take the transfer graph that we've analyzed, and we basically go through and find all the intermediate edges that existed in this graph. And we have to allocate them all. It has to be an all or nothing allocation, right? Because since it's generally a chain of things, if you start some, then you need to be able to flow all the way through in order to finish. The other catch is that we're going to be allocating from different memories on different nodes. And whenever you have multiple copies that are allocating from the same resources in potentially different orders, that's a standard recipe for deadlock. So I think where do we do this? Okay, so what we've done actually before we got to this point is we took all these intermediate buffer edges, and we built this array called ID alloc order, where basically we sort all the intermediate buffers by which memory, the IDs of the memories they're going to allocate in. And the reason we do that is that basically now it means that every copy, no matter whether it's from A to B or B to A, is going to allocate its intermediate buffers on, touch memories in the same order. And as long as you do that, and as long as all the allocations that a given copy is going to use within the same memory are done atomically, then you've got a deadlock-proof ordering, because basically means the older one will get all of its resources before the younger one, or at least you can never get a case where one copy has resources in memory X and another has resources in memory Y, and neither can get the other. But again, these allocations need to be sequential, or you can't you can't allocate out of order. So instead of sending the request to all the different memories we want to talk to, this is basically, this code is finding the first memory that we want to do allocations in and sending the entire allocation request for all the memories to that first one. And then that first one will pass it on to subsequent ones. And eventually what will come back is a list of all the allocations for this copy. And so here's the case of if we want from local intermediate buffers, well, then we can just do that here. Otherwise, we are going to build some tracking data structures and then ship off a request, an active message to some remote intermediate buffer saying, hey, let's go do these allocations. I guess there's also some code in here for the case where the allocation fails. That would be, so this is a case where an allocation immediately succeeds. It's also possible for an allocation to fail, right, if the intermediate buffers are oversubscribed. And that will also fall through to this and build the tracking structure. And eventually the intermediate buffer remembers which requests are pending and satisfies them in the order they showed up. And so it'll basically ping us when it's our turn to use intermediate buffer storage. The end result we get all the way down to here. We've now got all the intermediate buffers we need, and so now we can create what are called XDs or transfer descriptors. Transfer descriptors are for each hop in a copy, whether it's a hop in multiple copies or whether it's concurrent copies that are happening for different people of a larger copy request. Each of those hops is controlled by a transfer descriptor, which knows not both where is data coming from and going to and a bunch of parameters like that, but it also keeps track of progress of doing the copy. And so you can think of those as the actual agents of the asynchronous copy engine. And so first thing we need to do is we need to create them. And so this code here basically takes this transfer graph, this compiled template that we're going to use for instantiating a transfer graph, and goes through it, and basically for every single node in the graph creates a corresponding transfer descriptor and tells it, okay, this is precisely which input data you're using, which output data you're using, and the IDs of your peers, and turns this graph in this transfer descriptor, in this transfer graph, into an actual communicating graph of transfer descriptor objects. It's mostly, basically filling in blanks, and then the key call down here is this create transfer descriptor. And so this is the thing where every channel creates different kinds of transfer descriptors. And so once we figured out which channel we were going to use for a given hop in the path planning, that got turned into a factory function that knows how to create a transfer descriptor for that particular channel with all these parameters that we have that we pull out of the transfer graph. So if there's no questions on that, I will now switch over to talk about transfer descriptors and channels.
Can I ask a question? So like,
yeah.
Since the data actually like stays in the source instances, couldn't we like optimistically sort of start allocating buffers, intermediate buffers, and then, you know, if we detect a deadlock case, like fail and restart, or like try again and restart, because we haven't actually lost the data. Like any data that's in the intermediate buffers that we need to throw away because we hit a deadlock, right? Like it still lives in the source instance somewhere.
Yeah, I guess you could. The trouble is that we don't allocate buffers in data flow order. We allocate them in memory ID order.
Oh. But if you switch...
that's necessary. Yeah. No, we can't, because that's the deadlock problem, right? If I got a copy going from A to B and a copy going from B to A, right, we can't have the A to B copy allocate in A and the B to A copy allocate in
well,
B.
If you could detect the deadlock and restart the copy and redo the allocations, right? Like eventually hopefully somebody would win eventually. I mean, you have to worry about live lock, but...
yeah, and I mean, the other thing we talked about doing is this version here always allocates in order. Another optimization we talked about doing is you could try something where you actually attempt all your allocations concurrently. Mm-hmm. And if they all succeed, right, then good, you can go. Yeah. If any of them fail, then you have to unwind, from anything after the lowest memory ID that failed, you'd have to give back and then try to allocate in order.
Right.
It would be complicated, and it's not clear that it would have that much benefit, which is why we don't do it right now. Mm-hmm. But yes, in theory, it could be sped up a little bit. In practice, because actually, let me be careful, right? If you're doing a big multi-node gather, right? If you got copies that go between lots of different nodes, right? Yeah. Then even though any individual path only goes from one node to one other node, gathers and an overall copy can touch lots of different nodes, and so you could build logical cases where that copy, the intermediate buffer allocation request, has to visit every single node in the system, right? Sequentially, and that would be sort of unfortunate. Painful. But there's other reasons to discourage people from doing copies like that. Mm-hmm. so again, it hasn't come up.
Okay, let me ask one more question about the intermediate buffers. Do you reserve those in the realm graph, or do they have to be reallocated like when you replay copies in the realm graphs?
They currently are allocated for each instance of the copy.
Okay, so there's no like pre-reserved intermediate buffers for copies in realm graphs.
That's right. Okay. And again, there's a deadlock concern with doing that. There's also a concurrency concern, right? That if you had two instances of the graph and only one set of intermediate buffers, then you would serialize unnecessarily. This is actually similar to the problem if you look at CUDA graphs, right? CUDA graphs do allocate intermediate internal data for an instance of the graph, which means that once you instantiate a CUDA graph, multiple invocations of it are serialized. Mm-hmm. So there's a trade-off there. But the main reason we don't do it here is actually a deadlock concern, because intermediate buffer space can be pretty precious.
Okay, and how do you size the intermediate buffers? Like, are they just like there's a certain fixed size that you do for all copies, or do they are they variable size?
Basically, there's an upper bound somewhere in this code is a IB max size.
That's what I remember.
Which really, this guy here really should actually be lifted out into a configurable command line variable.
Okay, but it's like you just have like a single size for all intermediate buffers for all copies.
This is a single upper bound. If it turns out that we can look at it and judge that the copy is not even going to use 16 megabytes, then we don't ask for 16 megabytes. Okay. That's what this thing is doing here. We figure out the actual size we need, and then we clamp it to IB max size if we need to.
Okay.
And in theory, you might want to size this based on the bandwidth delay product of the channel that you're on.
Yes.
And in theory, we have that information now. We didn't used to have it. Now we have it. So we could be a little bit more fancy about doing this.
Maybe a little more aggressive at shrinking them down a little bit.
Right.
Yeah.
Right.
Yeah.
Yeah, we could do that. Okay, any other questions? I'm going to hop over to channel.h now, which is where transfer descriptors and channels live. So first, I want to talk about the transfer descriptor is right, as I said, is the object that represents a hop in a copy, and is the thing that knows, where's the data coming from, where's it going to, and all the and the current state of that transfer. I want to go through kind of the member data first a little bit to show you what the main pieces are. I'm not going to, I'll do it in groups. The first thing that's important is there's a queue that we want to queue ourselves into whenever we're ready to do work, and that basically is that's driven by the Realm background work engine. That each channel has a queue that ready transfer descriptors go into, and if that queue becomes unempty, then that channel asks the background work system to for service, and then the channel is allowed to make progress. So we put ourselves in the queue when we have copies that we can perform, and we go to sleep when we can't. We have a number of atomics that are used to track the total progress of a transfer descriptor. This gets very asynchronous in here because we can issue requests and they can be completed in other threads. So we need to be careful about race conditions around. And then there's two levels. So there's iteration, which iteration completed is basically have we initiated all the copies and all the individual pieces of the copy, and then transfer completed is have they really all completed. The next main thing is the set of input ports and output ports. And so a simple point-to-point copy will just have one input port and one output port, but other copies can have indirections, or scatters and gathers can have quite a few input ports or output ports. And each one represents basically one data source or one data sink. And so for each of those, we know, okay, what memory does that data live in? We have an object that will basically tell us what order to pull bits out of that memory. So that's this transfer iterator. If we are in a multi-hop path, we need to know who the transfer descriptor on the other side of the connection is, so we can do flow control. So that's called the peer in this thing, and not shown here. Okay, it's down here for some reason. Every transfer descriptor has its own global unique ID, and that's how we refer to our peers, because peers may not actually be on the same node, so we can't take pointers. So we use IDs. And the other thing we need to know is what index it is, because just knowing what peer it is, you don't necessarily know which output port corresponds to this input port. So these two together tell us how to tell our peer that we've made progress on a given one of its corresponding ports. If we're doing indirection, so gathers and scatters, then there will be another input port that is used to source the addresses that go into the indirection in this transfer iterator. And so this is the thing where we know, this is the thing that says which of the ports of the transfer descriptor is the indirection source for a given port. This one is in fact a source. Then these pieces here are responsible for doing flow control. And I'm going to skip over that for now because that's a topic that I'm probably just not going to be able to get to today. But importantly, intermediate buffers have a fixed size. As we said, we clamp them to 16 megabytes. And so quite often intermediate buffers will need to wrap around for large copies, which means you don't just need the forward flow control that tells you that data has shown up in the intermediate buffer and can be read and passed along the next hop, but you also need backwards flow control that says, hey, please don't overwrite the previous data until I get a chance to send it downstream. Additional complexity there is that copies don't always complete in order, so we need to be able to put back together completions that get out of sequence. And so that's what this sequence assemblers are doing, and they're used to basically track these counters of how many bytes have we moved, and whether we know what the total number of bytes is. And then last is which actual memory, if we're doing intermediate buffer, we need to know which memory it was and where in that intermediate buffer memory it was, so that we can free it when we're done. And then these last two things are I mentioned up here is a transfer iterator that basically generates a list of addresses to fetch from the source memory or write to for the destination memory. And it used to be that we consulted the transfer iterator for every single individual hop, every single individual piece of the copy. And there's a lot of overhead to that. So there's now a model where when the transfer iterator can generate a bunch of addresses and put them in this address list, and then we can basically take pieces off this address list in a much more efficient way than having to consult the iterator every single time. Another thing that is in here is if we are doing a scatter or gather, so a gather will have multiple input ports and a scatter will have multiple output data ports. We need some sort of control information to tell us which of the input ports to read from or which of the output ports to write to at a given time. And so one input port on the transfer descriptor can be responsible for carrying control information from the input, and a different one can be responsible for carrying control information on the output. And this is basically the control information effectively says, things like send a kilobyte, source the next kilobyte from port 1, or source the next kilobyte, 72 kilobytes from port 7, or throw away the next 28 kilobytes to output type things. And so that information comes from these ports, and then if we're not all the way done with whatever that, if it said do a kilobyte and we only have moved half a kilobyte, then we need to remember where we are in that kilobyte worth of control information. So that's what the control port state does. And the last, see that if a transfer descriptor is doing a fill, then we need the fill data. This important thing here is part of the asynchrony of making sure that transfer descriptors go into the corresponding queue when they're ready, but aren't pulled when they're not ready. And there's kind of the usual race condition of deciding that you're out of date and going to queue yourself or going to sleep, and then having somebody mark you as ready while you're doing that and keeping things from getting lost. So this progress counter is basically an atomic counter that's used to understand whether more progress can be made. Basically, every time new input data is ready or new space in an output is made available, we can bump the progress counter to indicate that we might be able to make more progress. Any questions? Anything that people think is obviously missing from this list? So this is the transfer descriptor is basically just a base class. Each channel will have its own specialization of the transfer descriptor. And so let me go find the simplest one, which is the memcopy transfer descriptor. So this one is basically the transfer descriptor used by the memcopy channel, and it's basically just going to override some methods. It doesn't need to add any other intermediate state. But it is these both the channels and the transfer descriptors are kind of specialized. So that a memory channel will only operate on memcopy transfer descriptors, which means that if you need to store other information there, you can. I guess it'll be the same on both, but if we go back and look at the methods on a transfer descriptor, there's a bunch, but there are it'll be easier to say on memcopy transfer descriptor. The key ones that show up are progress XD is the method that will be called when it is this transfer descriptor's turn to start emitting more copy requests. And so it gets called as told what channel and how long it gets to work. So this is a standard. We haven't talked about the background work system in RHEL explicitly, I don't think, Mike. But the basic model is that you're told to make progress and you're told how long you're allowed to run before you should give back the background worker thread to do other work. And then you return a function, Boolean, basically saying whether you completed all your work or whether you want to be re-enqueued for doing more work. The other important methods here are notify request, read, and write done. So if a request memcopy is actually fully synchronous, but other transfer descriptors will do things like kick off a CUDA copy, which is asynchronous, and need to be notified at some point that their copy is done, so they can mark that completion and move on to the next thing. And so that's a method that shows up in a lot of places too. So that's transfer descriptors. Now I'm going to go find the channel, which, just like transfer descriptor, is also a base class that basically describes the notion of, embodies the functionality for doing copies, from of a certain kind. Like memcopy would be distinct from HTF5 file IO. The basic thing a channel has is it's going to have some sort of queue for pending transfer descriptors. It's also going to have a knowledge of what kind of copies it's able to do, and so that's this supported path stuff that I want to talk about a little bit. And so a channel. So remember there was that find best single hop or something function. That's basically a wrapper that's consulting every single different channel in the system and asking them, hey, can you do a copy from this source memory to destination memory with these parameters? And it can answer 0 if it's not supported, or it can answer with an estimate of how long it would take that copy to be performed in nanoseconds, which is how we do the cost-based search of the tree. Instead of having every channel implement this method in a completely bespoke way, what we do instead is most channels instead basically store an array of what are called supported path objects, which basically describe patterns that they will support, either from a specific source memory to a specific destination memory, or from given kinds of memory to other kinds of memory, and then what the parameters are, what the bandwidth is, what the latency is, and fragment overhead is this thing that relates to the transposes and the like. This is the thing that says each separate copy will cost you this amount of overhead. So this allows for the cost of the packet header, or the cost of the CUDA driver API overhead for calling CUDA copy, for example. And so this is the thing that allows you to penalize copies that are discontinuous. It also says what's the maximum dimension, rectangle dimension it can copy in one go, and that relates to this basically. So if max source dim was 3, then it says, well, you can do a 3D rectangle for 1 cost of frag overhead, but if you wanted a 4D rectangle in that 4th dimension, it turns into an overhead for each hyperplane in that 4th dimension. In some cases, source and destination can be different. You can have cases that allow gathering, like HTF5 allows sparse source data but not sparse destination, for example, and things like that. So basically, most channels will fill in these supported path objects when it's constructed, and then let the stock supports path method just basically search through those for each given request and return whether any of the paths match, and if so, estimate the cost and that it'll take for that copy. And then, these two methods are the ones that manage the transfer descriptor queue, right? So I said each channel has a queue of ready XDs, transfer descriptors, and so this is the thing that says, okay, please go ahead and this XD is ready. Please go ahead and add it to the list. And then if one goes to sleep because it was waiting for input data or room for write output data, then this is the one that says, okay, go ahead and wake it up and kind of re-enqueue it. Helper functions for adding paths, the standard shapes, and that's basically what the root class of a channel looks like. I'm going pretty fast. I apologize, Mike. We may need to queue up around 3 for this, depending on
fine.
How many questions I leave unanswered.
Can I ask a question before you go on?
Yep.
So the transfer descriptor queue is effectively the background work item that gets called by the background worker threads. Is that right? Or
yes, effectively. I was going to do that next.
Oh, okay. Well, then I'll wait for you to do that, and then I'll ask my question about that.
Yeah. Okay. Yeah. So that's a good question. Let's try to find it here. There's some templating fun that goes with it, so I Yes. Yeah. So a channel owns a transfer descriptor queue, and that transfer descriptor queue is exactly a background work item. And so this is basically a list of ready XDs. I skipped over it, but the transfer descriptor, this is an intrusive list. The transfer descriptor actually declares a member data for being linked into this list, so we don't have to do any dynamic allocation to enqueue XDs. But yeah, this is the one that remembers which ones are ready. We've got a mutex to guard it. Importantly, there's a notion of ordered mode. And in ordered mode, we require that I'm trying to remember why we called it ordered mode. Basically, a queue that's in ordered mode is only allowed to be doing one copy from this, one transfer descriptor from the channel at a given time. So for example, HDF5 requires that all requests into libHDF5 be serialized. And so it's in ordered mode, which means that, let's say I have an HDF5 transfer descriptor queue with 2 items in it. We may pop, in the do work method, we may pop the first one off, but we won't re-enqueue ourselves right away because we don't want to execute again while we're still doing the first one, and so we stay in order. However, if you're unordered, say like the memcopy queue, then the do work method is a little bit different. What it'll do is it'll pop the first one off and it'll start to say, okay, let's do some memcopies. But if it sees there's other work in the queue, it'll actually immediately re-queue itself into the background work system. And so you can actually have multiple threads calling do work for the same transfer descriptor queue if it's not in ordered mode. And so that's how we can get parallelism for things like memcopies without without breaking the rules for things like libHDF5. So this is a templated class. It's templated on both the type of the channel and the type of the transfer descriptor, because as I said, remember those are co-specialized, and so they need to know about each other. From this queue, we build another template, which is most channels only have a single transfer descriptor queue. And so this basically separates out that functionality of a channel that's only going to have one transfer descriptor queue and therefore owns the queue. And again, exposes these methods. I told you about enqueue ready XD and wake up XD were methods defined on channel. This is where they get overridden for something that's going to have a single channel to feed. I'm actually not sure if there's any channels right now that don't inherit from single XDQ channel, but in theory you could. What we do for, say, host to device versus device to host copies is those are currently 2 different channels. In theory, it could have been one channel with 2 different queues. But at least today, almost everything uses a single XDQ channel. So pretty much everything is going down this path, and as you said, it's a background work item. So I probably didn't answer the question you were going to get to, but now at least there's context.
Okay, so the question I was going to ask was actually, so when this background work item is actually invoked, usually the background work items get like a timeout, and right. I'm guessing these XD queues, right? They're going to call progress XD on the things right. in their queue.
So what do work is going to do is it's going to pop the first thing off of its queue, and it's going to maybe re-enqueue itself right away, re-enqueue the work item right away if we're not in ordered mode.
Right.
So call that progress XD on that XD, which will either use it the whole time, in which case we pop back out, or if it either completes or stalls out due to flow control before the time has elapsed, then this do work method will be able to take the next XD and do some work on that one too.
Right, but progress XD doesn't take a timeout, right?
It did.
It did, but it doesn't anymore. Or
no,
I was just looking at the progress XD down below.
Oh wait, okay, one sec.
Oh, this one does. Okay.
Yeah, there's a couple decoys.
Yeah. Okay. All right.
Yeah, but this is the right one.
Okay.
So anything that's working with that single XDQ channel is using this version. Let me go find that other one, because that was actually some wraparound. Where was that one? Yeah. See, remove.
Yeah.
Yeah. Basically, you never call progress XD
with that. Yeah.
With that. Yeah. Yeah. So
Okay.
this is dead code. I can't remember what old piece needed it. But yeah.
Okay.
Yeah. All the real ones take a time limit.
Okay. And then that's like guidance though, like they're allowed to overrun the time limit, or do you have strict barriers on how long? I mean, it's kind of up to the transfer descriptor to kind of like abide by that limit.
Yeah, that's right. It's advisory.
Right. So modules that implement their own transfer descriptors for certain memory channels or for certain channels might not abide by it.
If you write, you should abide by it. And
you should.
The place where it gets a little fuzzy is how often should you check it?
Yeah.
So for example, with the CUDA stuff, what Corey and I worked out is we should check it after each call into the driver. If you want to batch up a bunch of things that you're going to do on call to the driver, go ahead and do all those without checking. And then, if the driver calls are the relatively expensive things there, so check after each one of those to make sure you're not overrunning too far.
Okay.
So for example, if I get into the memcopy one, you'll see that the memcopy one, the other thing it does is it actually limits how big a copy it will do in one go, since it is a synchronous copy.
Right.
So that it doesn't overrun. It doesn't actually look at the timeout and try to divide how many bytes can I copy. It just breaks it up, I think 256 kilobyte chunks, which are kind of big enough to warm up prefetchers and stuff, but not so big that they'd
overrun the copy.
Massively overrun the time limit.
Yeah. Okay.
There is some logging in the background work system that is supposed to complain if something runs way over its time limit, but I think that's actually not enabled because not everything is able to respect the limit yet. But you could imagine going forward having some kind of telemetry that tells you the given work item is routinely overrunning the estimates it's
given. Right. Can you just give us what is like one example of something that is not abiding by the limit right now? I know it's a distraction, but yeah, David.
Let's see. I think I've gotten the big ticket ones. Some of the depth part things are probably not.
Okay.
I think probably really extensive dependent partitioning operations don't know how to go partially. Okay. So yeah, now let me do the simplest concrete example, which is the memcopy channel. In the construction of the memcopy channel, as I said, the main thing most channels do is they add paths so that the standard supported path stuff works. And so this is the thing that basically says, find all the local CPU memories and claim that we can copy from any local CPU memory to any other local CPU memory with these hacked up bandwidth and latency numbers. There's been an effort by other folks to go through and improve some of these numbers to actually be real. Clearly, these ones haven't been gotten to yet. And the other thing is there's a complete lack of NUMA awareness here as well. So all of these things are hacks. They're kind of rough orders of magnitude, but they're designed to basically to understand if the orders of magnitude are right, then hopefully you won't get things choosing completely wrong paths. And you might have misestimated the cost by a factor of 2, but as long as it's not a factor of 10, then you're probably not choosing the wrong path. And so the constructor is basically adding paths and then adding our queue, that transfer descriptor queue, to the background work system, so that we can queue up things. I said that most channels rely on the base channel supports path method. There are a few exceptions here and there. Like for example, memcopy claims that it handles serialization, but it doesn't actually want to handle simultaneous serialization and deserialization. So it has a special case that says if they ask for that, then say no. Otherwise, let the normal checks work. I mentioned each channel needs to know how to create its own kind of transfer descriptor. And so every channel will have a create transfer descriptor method, which takes this info and constructs a transfer descriptor of the right type. Then this submit method is actually the old way that channels work, so I'm not going to focus too much on it. I want to focus on the new way, because that's how people should write new channels. Just briefly, it used to be that the transfer descriptor was responsible for making requests, and then the channel is responsible for actually implementing those requests. So there was yet another level of indirection in this of queuing things up. And we found that most often that was unnecessary overhead. So the new model now is the channel is sort of the container, but transfer descriptors will do their own progress instead of queuing up requests for the channel to service explicitly. But so if you see things using the submit method, this was the old path where a transfer descriptor would create requests, and then this is the channel actually submitting them to whatever system performs it. So we're going to skip over that. And once we skip over that, we find that that's basically all there is in our channel. All right, so the main two things that a custom channel needs to do, coming back up here, is it needs to know how to create transfer descriptors, and it needs to know how to define the paths that it supports. And now all the rest of the functionality is in the transfer descriptor itself. And unfortunately, I'm at the top of the hour. So I think probably I should pick up next time, starting with memcopy transfer descriptor. But I can take a few last questions now if folks have them.
I'm all
Does the quietness, mean I went too fast or too slow, or that nobody's actually awake today?
Okay, I have a question about the find the finest path. So
sure.
So if we consider the ongoing communications, I mean, do you think we should consider the ongoing communications in the find the fastest path?
No, that's a great question, right? This find fastest path is completely static. It's basically saying, assuming an empty system, what would the path be?
Right.
Understanding contention would be really, really hard because for two reasons. First of all, we're calling this long before we're actually doing the copy, right? We want to have a plan in place before the data becomes ready, so that as soon as the data is ready, we can start copying. But that means we don't know at the time we're planning the path what other things are going on at the time we actually do the copy. We also don't know what flow control is going to be like. So even if we did know what copies are running concurrently, we don't know whether they're actually utilizing the system well or whether they're bottlenecked by some slower path in their copy. So there's no attempt right now made at understanding congestion here. It is a limitation though, so it's worth thinking about if there's heuristics we could use either in, one thing you could imagine is find fastest path recognizing that there's multiple viable paths that are about the same speed and doing some sort of stochastic spreading over them, saying this time we'll use this path and next time we'll use that path, so that different copies might run different paths. Another thing you could do is you could at least look at the contention with the other copies, the other hops being done in the same copy. All right, so if Legion gives Realm a copy that says copy these 100 fields to these other 100 fields, then in theory, you could teach find fastest path to understand load balancing between those 100 fields at least, so that they don't all follow, use one NIC. We could spread them out over the NICs, so you could definitely do that. You could also imagine some amount of contention handling down in the transfer descriptor that basically says, hey, this channel looks hot. Maybe I should have a way of, bouncing it off some intermediate thing. And this is how, for example, Dragonfly works. But that, that's down at the lower level. You can imagine some sort of intermediate thing for that too. But that's a great question because we don't do it now because it's really hard to do an asynchronous system, but it doesn't mean it's impossible to do better than completely static. So if you have ideas, I'd love to talk about those.
Okay, or even though we don't know the ongoing communications, but we know that there are communications because we can record all the communications happens in the same node, I guess, like in and out of the node.
But you can't know when they're going to happen, right? Because each of them has preconditions, and you don't know when the preconditions are going to be satisfied.
Oh, okay, I see. Right. Okay, makes sense.
Now. That brings up another wrinkle, which is something that Realm doesn't do with preconditions. It doesn't make any attempt to estimate when they might be ready and do kind of deadline-based scheduling type things. But you can imagine either with hints from above saying how long an operation is going to take, or in the case of copies with analysis like this saying how long the copy should take. You can imagine Realm making estimates of when things might get done and doing some attempt at looking in the future to come up with slightly more optimal schedules.
Okay. Thanks.
Sure. did you still have a question?
Nope, I'm done.
Okay. Well, what do we call it a day for now? And
We'll do another
when
one.
you decide, if and when to do a round 3.
Yep.
I can definitely consume another hour. So
Sounds good.
okay. Thanks for your attention, everyone.
All right. See everyone next week.